Hi friends, already we have completed the chapter number 1, that is the chemical kinetics. From today we are going to start the next chapter, that is a investigation of molecular structure. So here let us consider the syllabus of the investigation of molecular structure. So it contains molar refraction, electrical polarization of molecules, permanent dipole moment, determination of the dipole moment. So here we are going to discuss the various method for the determination of the dipole moment. Then here molecular spectroscopy, that is the molecular spectra. So here in the molecular spectra we are going to study the rotational spectra, vibration spectra and the Raman spectra. So here this is the syllabus of investigation of the molecular structure. So let us begin with the introduction. So friends, the substances are made up of molecules which are of same or of different elements. The formation of molecules takes place by chemical combination of atoms. Thus, for a given substance, the composition of molecules is very important and can be determined by chemical analysis. From the study of reaction, here one can find out the sequence of atoms in the molecules or sometimes the molecular geometry. But in order to know the molecular structure, the information of bond length, bond angles, polarity of bonds, internal molecular structure and atomic motions should be known. Such information can be obtained by using the various physical methods. However, there is no single method for establishing the structure of molecule. In this chapter, we are going to discuss some methods like dipole moment, measurements and molecular spectroscopy to study the structure of molecule. So, here first of all let us consider the physical properties. So, here there are mainly 4 types of the physical property: intensive property, extensive property, additive property and here the constitutive property. So, let us consider one by one. So, number 1 is the intensive property. So, what is meant by intensive property? So, here these are the properties which do not depend on amount of the substance present in the system. So, here such properties are called as intensive property. Let us consider here example: density, specific gravity, refractive index. These are the some examples of the intensive property. So, friends, here density is the intensive property. If we determine the density of 10 ml water as well as the density of 100 ml water, the density of the both the waters is same. So, here same way if we determine the specific gravity of the various waters, again it is the same. Similarly, refractive index, if I have 1 ml water and if we have 10 ml water, if we determine the refractive index of both the waters, finally here the refractive index is the same. So, here refractive index, specific gravity, density are not depend on the amount of the substance present in the system. So, here these properties are intensive properties. Second one is the extensive properties. So, here extensive properties are the properties which depend on amount of substance present in the system. For example, here mass, weight, volume, these 3 are the extensive property. Suppose here if we have the 2 beakers, the capacity of the first beaker is 50 ml and the capacity of the second beaker is 100 ml and both these beaker they are full of water. So, here we can say that the water present in the first beaker it is a 50 ml and the water present in the second beaker it is a 100 ml. So, here the volume of the water it depend on the quantity of that water. So, here the volume it is a extensive property. Second example is the weight. Suppose here again we have the 2 chalks. The weight of first chalk is 5 gram. Then here the weight of 2 chalks it is a 10 gram. So, here we can say that the weight of first chalk it is a 5 gram and the weight of the second and first and second chalks it is a 10 gram, because here weight of chalk it depend on the quantity of that chalk present in the system. So, here weight, mass, volume, etc. are the extensive property. So, here the intensive property as well as the extensive property. Next property is the additive property. So, here these properties are some of the corresponding properties of the individual constituent of the system. So, such a properties are called as the additive property. So, here when the property of the molecule is the sum of the properties of the constituent atom, so it is called as the additive property. So, here the best example of the additive property is the molecular weight. So, here the molecular weight it is the additive property because molecular weight is the sum of the atomic weight of the atoms of different element present in the molecule. So, let us consider one example here, methyl alcohol. Suppose here we have to find out the molecular weight of the methyl alcohol. So, the formula for the methyl alcohol is the CH3OH. So, atomic weight of carbon is 12, then atomic weight of hydrogen is 1, there are 4 hydrogen. So, 12 plus 4 that is 16, and atomic weight of oxygen is 16. So, 16 plus 16 that is a 32. So, here the molecular weight of the methyl alcohol it is a 32. So, molecular weight it is the additive property. Then fourth one is the constitutive property. So, here the constitutive property it depends on the arrangement of atoms in the molecules. So, here the best example of the constitutive property it is the optical activity. So, here friends, which substances are optical active? The substances which contain asymmetric carbon atom, the organic substances which contain the asymmetric carbon atom, such substances they show the optical activity. So, here what is the asymmetric carbon atom or chiral center? So, here if the 4 different groups are attached to the carbon, then such a carbon it is called as the asymmetric carbon atom, and if the asymmetric carbon atom is present in the organic substance, then such a substance is optically active. And what is my optically active substance? So, here when the plane polarized light, when it passes through the optical active substance, then there is a change in plane of polarization. So, such a substance it is called as the optical active substance, and the property it is called as the optical activity. So, here the optical activity is present in such a compound if there is only asymmetric carbon atom. So, here optical activity it is the constitutive property. And the last one is the colligative property. So, here the colligative property of the solutions it depends on the number of solute particle present in the solution, and it is not depend on the nature of the solute particle, but here the colligative property is the property which depends upon the number of solute particle present in the solution or in the system. Such properties are called as the colligative property. Friends, there are 4 colligative property. Already we have discussed the colligative property in the SY BSc class. So, here the number 1 is the lowering of vapor pressure, number 2 is the elevation of boiling point, number 3 is the depression of freezing point, and number 4 is the osmotic pressure. So, these are the 4 colligative properties. So, these are the 5 physical properties, but here above property does not give any idea about the bond length, bond angle, then solute solvent interaction, then hydrogen bonding, resonance, etc. So, such properties we are going to study in this chapter. So, here the physical properties. So, let us consider the first point, that is the first property, that is the molar refraction. So, here first we are going to define what is meant by a refractive index, and then we will consider what is by molar refraction as well as the specific refraction. So, here let us consider this diagram. So, here this is the incident rate. So, here incident rays, this is the refracted rays. So, here when the beam of light passes from one medium to another, one medium means from rarer medium to the heavier medium. So, here then it undergoes a change of the direction. The directional change of light is called as the refraction. So, here the rarer medium or the denser medium. So, here the rarer medium is the air, and here the denser medium, suppose it is the water. When the light radiation, when it passes from the air to water, so what happen? This is a normal line. This is the normal line. So, here this incident ray it is refracted toward the normal. What is the meaning of refraction? Refraction means bending of light. So, here the I is the angle of incident, and here the R is the angle of refraction. So, here when the light radiation when they are passes from the rarer medium to the denser medium, they are refracted toward the normal, and this angle of refraction it is R, and angle of incident it is a I. By considering these two, we are going to define the refractive index. So, here according to the Snell's law, so here as per Snell's law, refractive index n is equal to sin I upon sin r. This ratio is constant, and that constant it is called as the refractive index. So, this is the definition of the refractive index. Then here refractive index can also be defined as a ratio of velocity of light in vacuum or air to the velocity of light in the denser medium. This is another definition of the refractive index. So, here friends, refractive index of any liquid or solution, it can be measured by using the Abbe's or the immersion refractometer. Refractive index of liquid or solution, it depends on the wavelength of light as well as it depends on the temperature. So, these are the two main factors which affect on the refractive index, that is the wavelength and the temperature. Then friends, Lawrence and Lawrence defined the term molar refraction in 1880. So, here as per Lawrence and Lawrence, the first specific refraction RS is equal to n square minus 1 divided by n square plus 2 into 1 by d, where RS is the specific refraction, n is the refractive index of that liquid or solution, and the d is the density of that liquid. Then here n square minus 1 divided by n square plus 2 into 1 by d. By substituting the value of the n, that is the refractive index, and the density of that liquid, we can find out the specific refraction, and the unit of the specific refraction is ml per gram. And here the specific refraction, it is the same for both the liquid and the gaseous state of the substance. So, here when the specific refraction is multiplied by the molecular weight, we get the molar refraction. So, Rm is equal to Rs into its molecular weight. So, this formula can be written as n square minus 1 divided by n square plus 2 into m by d, where m is the molecular weight of that substance, d is the density, and small n it is the refractive index of that liquid. Then here the molar refraction, it has the unit of the molar volume, that is a ml per mole. So, here the molar refraction, it is expressed in terms of the ml per mole. So, here the molar refraction and the molecular structure. So, molar refraction it is also very useful to determine or to study the molecular structure. So, here molar refraction is partly additive and it is a partly constitutive property. Already we have discussed what is by additive property as well as what is by constitutive property. So, here molar refraction, it is a partly additive and partly constitutive property. So, here molar refraction, it depends upon number and nature of the atoms present and also on characteristics of the bonding. So, molar refraction can also be used to check the structure of the molecule. So, here in this table, the molar refraction contribution to the sodium D line for the various bond element, it is given in the table. For example, when we consider the carbon, the molar refraction contribution of the carbon is 2.418, hydrogen 1.10, it is also called as the atomic refraction equivalence. So, chlorine 5.967, bromine 8.865, then here oxygen in hydroxyl group, its contribution or its atomic refraction equivalence, it is 1.525. When the oxygen is present in the carbonyl group, its contribution is 2.211. So, oxygen in ether, it is 1.643. So, with the help of this data, we can find out the molar refraction. So, here the molar refraction is also determined by using the formula Rm is equal to n square minus 1 divided by n square plus 2 into m by d. Just substituting the value of the m, d and n, we can find out the refractive, we can find out the molar refraction of any liquid or any substance. So, similar way here, by considering this atomic refraction equivalence or this is a this contribution, we can find out the molar refraction of any compound or any substance. So, let us consider one example here. So, calculate the molar refraction of acetic acid at 22.9 degrees Celsius having the density 1.046 gram per cubic centimeter and the refractive index for sodium light, it is 1.3715. So, molecular weight of acetic acid is given, it is a 60. So, here we know that Rm is equal to n square minus 1 divided by n square plus 2 into m by d. So, substituting the value of the m is given 60 D is the density, it is also given 1.046 gram per ml or per cubic centimeter. N is the refractive index. So, here the refractive index is also given 1.3715. By substituting all the value, we can determine the Rm, and that Rm is equal to 13.0322 ml per mole or cubic centimeter per mole. So, by using this formula, we can calculate the Rm. Similar way here, by using the table. So, here the molecule which is given is the acetic acid, and its formula is CH3COOH. So, there are 2 carbon. So, contribution of the carbon is 2.418. So, 2.418 multiplied by 2, it is a 4.836. So, in acetic acid there are 4 hydrogen. So, here 4 into H, that is a 4 into contribution of hydrogen 1.110, that is a 4.400. So, there are 2 groups, there are 2 oxygen, one in ketone and one in carboxylic group. So, oxygen in OH group. So, here the contribution of oxygen in the OH group, it is a 1.525. So, 1 into 1.525, it is a 1.525. Then one oxygen in the carbonyl group, its contribution is 2.211. So, here 1 into 2.111. So, it is equal to 2.222. So, here when we add this, so here we will get the molar refraction value for the acetic acid, and here the molar refraction of acetic acid as well as the observed value and the calculated values, both the values are nearly same. So, friends, the molar refraction can be applied to gases, liquids and the solid also. The molar refraction of gases is usually found to be identical with that of corresponding liquid. That means, here if we determine the molar refraction of the liquid substance, and if that same liquid substance is converted into the vapor state or the gaseous state, and if we determine its molar refraction, the molar refraction values are same. That means, here molar refraction for the liquid and the gas, both the values are same. So, the molar refraction of solids is found by dissolving them in the solution and measuring the density of the solution. So, friends, here suppose we have to find out the molar refraction of the solid substance. What is the procedure? First, here we have to prepare the solution, and here then we have to measure the density of that solution. So, molar refraction of the solution, it is denoted by symbol R12, and the formula is R12 is equal to n square minus 1 divided by n square plus 2 into capital N1 into capital M1 plus capital N2 into capital M2 divided by D, where D is the density of the solution, N is the refractive index of the solution, M1 is the molecular weight of the solvent, M2 is the molecular weight of the solute, and here N1 is the mole fraction of the solvent and N2 is the mole fraction of the solute. By substituting all this value, we can determine the molar refraction of the solution. So, here this refractive index N, it is determined by using the Abbe's refractometer. So, directly we can substitute the value of the N here. M1 and M2 are the known, because these are the molecular weight for the solvent and the solute. N1 and N2 are also known, because these are the mole fraction for the solvent and solute. D is the density. It can be measured with the help of the specific gravity bottle, or it can be measured with the help of the pycnometer. By substituting all these values, here we can determine the molar refraction for the solution. So, here the relation between the molar refraction of the solution with that of the molar refraction of the solvent, that is R1, and the molar refraction of the solid, that is R2, it can be given by the equation, that is R12 is equal to N1 R1 plus N2 R2. Again, here N1 and N2 are the mole fraction of the solvent and the solute. These are the known quantity. Here R1 is the molar refraction for the solvent. Again, by using the formula, we can find out the R1, and we know the R12. So, directly we can substitute the value of the R12 here, N1, R1, N2, and we can find out the molar refraction for the solid or molar refraction for the solute. So, here the R2 is equal to R12 minus N1 R1 divided by N2. By using this formula, here we can find out the molar refraction for the solids. So, here the when we determine the molar refraction of the liquid, it is the same for the gaseous substance, and molar refraction of a solid substance, it can be determined by using this formula. So, friend, in first lecture we have discussed the various physical properties, then here the what is meant by refractive index and what is meant by molar refraction. So, in the next lecture we will consider the next point. Thank you.